In the last lecture, I discussed with you how to solve trusses and frames using the method of sections. In this lecture, we're going to discuss the method of joints. The method of joints is most useful when you're looking for all of the members. If you're looking for just a few forces and a few members, I would recommend using the method of sections in most cases. But if you have to solve the entire truss or frame, the method of joints is probably a better way to do it. The procedure is as follows. You begin with drawing a free body diagram of the entire frame, then label each joint. And then what you want to do is locate the joints with one known and 3 or less unknowns. So you don't want more than 3 unknowns. You might have to solve for support reactions, you might not. It depends on the problem. Then for each of those joints, you're going to draw a free body diagram of just that joint. Some of those joints might require simultaneous equations depending on the number of unknowns that you have. Then you're just going to solve the joint. In most cases, you're going to use some of the forces in the x and some of the forces in the y with each joint to solve for all the unknowns at that joint. Then you'll move to the next joint and you'll repeat the process. One of the tricky things about this particular method is that every single answer is dependent. So after you solve for a couple of forces within a couple of members, you're going to then solve the next joint and you're going to use the answers from the previous one to solve that one. That makes checking your work very tricky, and it makes it very important that you have done everything correctly because there is no good way to check your work. Finally, you report your answers. Once again, you'll report the answer with magnitude and mode. That'll be either tension or compression. As a last point, I want to mention that there are zero force members in some cases, and if you know the zero force members or if you see them, that'll make your work a lot easier. So let's just, for example, take a look at a joint. Let's suppose that there's a joint here, and let's suppose there's a force going up and a force going down. Let's also suppose that simultaneously there's a force going this way. And we'll call this A, B, and C. You'll see if we sum forces in the y direction and apply static equilibrium, you'll find that A equals B. Okay. However, if you sum forces in the x direction, there's only one unknown. And actually, there's only one force. So that means that C is 0. Okay. And that zero force member statement is a big help. It's also true if we look at this situation, though. If there are two collinear members, so let's call this A prime, and let's call this one B prime, and let's suppose that there's a member diagonal over here. We'll call that C prime. This might not be quite as obvious to you as the first situation. However, again, even though there's 3 unknowns, 3 forces acting in the y direction, if we sum forces in the x direction, the only force in the x direction is C. So that once again means that C prime is 0. So it doesn't matter what angle this third force is acting at. If there's only 3 forces acting on a joint, and 2 of them are collinear, the third one will always be 0. If you see that on any type of method of sections or method of joints problem on any frame, you will know that that third member is 0. So this problem, we're given a frame with a couple of forces acting on it. It's pin connected at points A and E, and we're asked to find the force in each member. As I mentioned earlier, since it's asking for the force in each member, the best method to use here would be the method of joints rather than the method of sections. After labeling all of our forces and angles, we're also going to need to put on our support reactions. So here at point A was a hinge, and here at point E was a hinge. Each of those hinges is going to produce 2 unknowns, an x and a y. Now I'm going to need to solve for a couple angles too. I'm going to need this angle beta right here. That angle is the same as this angle right here and that angle. I'm also going to need to know delta. Now, as a quick note, the first time I solved this problem, I assumed that delta equaled alpha, that it was 45 degrees. It's very close, but that is not actually correct. So I want to just remind you to be careful about your assumptions when you're working with angles and distances. So to solve for beta, we've got this right triangle here. It's a 5, 12, 13 right triangle. And so I can say that the tangent of beta equals opposite over adjacent, so that'd be 5 over 12. And then we'll find that beta equals 22.6199 degrees. If we look at this grouping of angles over here, you can see that all three are going to add up to 90. So my angle delta is going to equal 90 degrees minus 2 beta. Delta equals 44.7602 degrees. Next, we need our global path to solution. And in this solution global path, I'm going to try to figure out, okay, how am I going to solve all of these unknowns? Now, we could start with the support reactions, but the problem is there's a lot of unknowns. In the y direction, there are 2 unknowns. In the x direction, there are also 2 unknowns. It's going to be hard to solve those. On a problem like this, I would encourage you not just to look at the support reactions. I mean, you're always welcome to look at them and figure out, okay, like you could sum moments at point E, or you could sum moments at point A, and those would let you find F4 and F5. But look around the truss too and see if there's any other points that you could solve. So for example, up here at joint C, I have one known, which is F1 acting in point C, and I have 2 unknowns. I don't know CB, and I also don't know CD, but I can solve that. So that is actually going to be my first step. After solving joint C, I will know CB and CD, and so next I can come down to joint D. At point D, I would know CD. I can then use that to find BD and ED. So that's my second step. And then after that, I still have 2 more unknowns. I don't know BE and I don't know AB. And the place where those intersect is joint B. Once again, all these answers are going to be dependent. So for example, when I look at joint B, I will use CB to solve for the other forces. So it's really important that you make sure that all your answers are correct because you're using them to solve for others. So in this problem, you don't need to solve for the support reactions at all. Actually, you can get away from it entirely. That is not always the case, but it just happens to be the case here. So we're going to start with joint C. Acting on joint C, we have F1. We also have CB. We also have CD. I want you to notice that I've drawn both CD and CB in tension. That is not accidental, nor is it optional. And we also need to know this angle here, which is beta. It equals 22.6199 degrees. All right, so now we want to look at this particular diagram. It's a free body diagram. There's 3 forces acting on point C, and we want to ask how many unknowns we have in each direction. So if we look at the x direction, there's only one unknown. CD has an x component, we don't know what it is. If we look in the y direction, there are 2 unknowns. CB and CD both have y components. So we're going to want to start with the x direction. We'll start with our assumption of static equilibrium. CB has no x component. If you want to write it down and then cross it out, that's fine either way. So then 0 equals F1x is a positive F1. CD's x component is also positive. That's a CD. And the x component would be CD times sine beta. Solving this for CD is going to give us this. CD equals F1 negative divided by sine beta. Plugging in the numbers, we will find that CD equals 780 pounds in negative, which means compression. If you want to write the step above it saying CD equals negative 780, that's fine. So now we can do the same thing to the y direction on this same joint. When we plug the values in, CBY is a negative CB, CDY is a negative CD times cosine beta. Okay, because CD is drawn going down. So CB is going to equal negative CD times cosine beta. Now here's where you have to be especially careful with the method of joints. CD we already solved for, and we saw that it was in compression, which in this case is negative. It's the opposite of what I have drawn in the diagram. So when I plug my value in for CD, that is a negative 780 pounds times the cosine of 22.6199 degrees. So it's actually positive. If we look over here, we solve for CD in the x direction, we got a negative answer, which means that CD is going in the opposite way we have it drawn. That would show a positive y component. I suppose it really doesn't matter how you account for that change of sign. This is just the way that makes most sense to me. What I do is I plug in and use all my math based on the way I have the diagram drawn, and then when I go to plug in the actual value, I plug in the actual value I got, including the sign. Please do not go back and change your diagram. Let's say I get to this point and I'm like, oh hey, I realize that CD is negative. I've drawn it incorrectly. So I go back up here and change my diagram and have CD going up. That's confusing because we always assume our unknowns as tension. And second of all, that makes all your work here wrong, because if CD is then going up, that means the x component's negative and I got to flip all the signs. That's an unnecessary amount of work, so please don't do that. CB equals 720 pounds in tension. So once again, the tricky part about this is that all of the answers are dependent upon the answers in the previous section. So now when I use CD and CB in any other diagrams, they are no longer unknowns in this problem from the perspective of this problem. They are now knowns, and I have to include their senses correctly. So here's my joint D. I know CD, I don't know DB, I don't know DE. Now you can solve this using two equations to unknowns, applying static equilibrium to the x and y directions. But the easier way is if you see that this is going to be a zero force member. DB is a zero force member. How do I know that? Well, CD and DE are collinear. And because of that, I know that their values are going to be equal because there's no other forces acting in this diagram. Let me redraw this in a different rotation. If we rotated these forces so that CD was vertical and DE was vertical, and DB was horizontal, you can see from this, if we sum forces in the x direction, DB is going to be 0. If we sum forces in the y direction, CD is going to equal DE. So that tells me that DB is a zero force member. Once again, you know that when there are three forces acting on a point, two of them are collinear, the third one is going to be 0. And you could actually just state that with another Roman numeral saying zero force member. DB equals 0 pounds. That is a required step, that you actually state that it's a zero force member if you're not going to use this static equilibrium. When you do this, please make sure that you understand what a zero force member is and don't make mistakes on calling them zero force members. There have to be only three forces acting on a point with two of them collinear. Now at this point, it doesn't really matter if I apply static equilibrium to the y or the x direction. I'm just going to do it to the y. Okay, and in this statement, dby is going to be 0 because db is 0. Now I want to remind you though that there's a big difference between a zero force member and no force at all. The only reason this force is 0 is because there's nothing that's going to develop a force in it right now, but we could give a different loading situation in which the force in dB would not be 0. So that is important that you state that. So 0 is CDY is a negative CD times the cosine of beta. DEY is a negative DE times the cosine of beta. And you can see the cosines of beta, we can divide both sides by cosine beta and they're going to cancel out. So DE equals a negative CD. which means DE is 780 pounds, also in compression. Note here that when I drew CD, I drew it in compression. It's important that you do that. It's important that as soon as you find a force, you draw it in its correct orientation so that you can get the answers right for the rest of the problem. All right, so here's joint B. I've got CB, DB, and F2 all acting on it, and I know the value of all three of those forces. I don't know AB, I don't know EB. Now I need to solve for AB and EB. Before you do that, you want to stop and say, okay, how many unknowns do I have in the x direction? AB has an x component, EB has an x component, so that's two unknowns. How many unknowns do I have in the y direction? AB and EB both have a y unknown, so it doesn't really matter where you start. Okay, CB has no x component. Likewise, DB's x component is 0. So now F2x is a positive F2. ABX is a negative AB times cosine alpha. EBX is a positive EB times cosine delta. That equation has two unknowns. We can't solve it yet. So I'm just going to call it equation A and move on. So 0 equals F2y plus CBy plus DBy plus ABy plus EBy. F2 has no y component and DB's y component is 0. That means 0 equals CB minus AB times sine alpha minus EB times sine delta. That equation also has two unknowns, and so we just need to label it and move on. Now at this point in time, I'm going to choose to work with equation A. So that equation then becomes 0 equals tangent of delta times F2 minus AB times cosine alpha times tangent delta plus EB times sine delta. If I take these two equations then and add them together, this top one is the modified equation A down here. This bottom one is just equation B. If I add those two equations together, you're going to see that I'll have a positive EB times sine delta and a negative EB times sine delta, and those two terms will cancel out. So then this equation becomes 0 equals CB plus tangent of delta times F2 minus AB times the quantity of cosine alpha times tangent delta plus sine alpha. Solving this equation here for AB is going to give us this. And now we can plug the numbers in. And we'll find that AB is 722.492 pounds in tension. Now I'll take my equation A again and rearrange and solve it for EB. Now you might wonder why I chose to work with equation A. I have a little more confidence in equation A. And that's because F2 is in it. F2 was one of the original given forces. Equation B is not more or less challenging to use, but it doesn't have any of my givens in it. So in order to give just a little bit more validity to my answer, I went ahead and used equation A because it's got that known variable already in it. Now it's true I'm still using unknowns in this problem. I'm still using AB to solve for EB, but the fact that I'm using F2 in there, as I said earlier, gives me a little more confidence in the final result. Plug in the numbers in, we will find that EB equals 296.988 pounds in tension. At the end of the problem, all my answers go in the answer box, both the value, magnitude, as well as the mode. I do want to note this last part. If you've got multiple frame members that are the same value, it's acceptable to say that they each equal each other, as in this. Just make sure that the value and the mode is the same. But when you're solving for an entire truss, it's likely that you're going to have multiple members that are the same value.